Лекцию сегодня прочитает Фабрис Коллард, который сотрудник Ocean Data Laboratory во Франции, в городе Брест. Это недавно образованная лаборатория, которая, предполагается, будет сотрудничать с нами в будущем. Ну и Фабрис также является профессором кафедры ЮНЕСКО. Ну, мне, может быть, излишне говорить, но Фабрис является реально одним из ведущих специалистов в области скаторометрии, восстановления ветра по полям, сааровских изображений и так далее. Ну,
okay, please. Thank you, Vladimir, for introduction. So, I will present today some basic about scatterometer winds and SAR wind. So here it's written scatterometer, but the second part is with a SAR wind. So our overview is first introduction, then definition of the normalized radar cross-section, which we call sigma 0, which is the basic measurement from the scatterometer, from which we derive wind. Then some element of geophysics with the GMF that are used to transform the sigma 0 into a wind. And after also some source geometry of the orbit of the satellite, the scatterometer, some words on accuracy and resolution, and the limitation of the measurements, and some application. So first of all, just to show an example of scatterometer wind. So here we have some polar laws that are developing, and we see that we can have observation at different time with the scatterometer to follow such weather pattern. And so you can see on the right that the measurement is not covering the full globe. As you see, the red flags are not everywhere. Like the blue flags are from the numerical model. So the numerical model is at almost the same time as the scatterometer. There are some differences, but we have much higher resolution information on the wind from the scatterometer. So this is another typical case in Aegean Sea, where you have scatterometer wind. So of course it's only over water and not too close to the coast, because there might be some contamination of signal if you are too close to the coast. As you see, the pink dots that are closer to the coast are usually of less quality with the scatterometer, and this is why we will produce the SAR wind also to get closer to the coast. So then about the normalized radar cross-section. So this is just for illustration of the wind speed and wind scales. So as you see, the scatterometer will be able to measure the force of the wind based on, in fact, the effect of the wind on the surface. And you can see from this Beaufort scale picture that there are strong effects of the wind on the surface. So first, you see, so when the wind is calm, so this is 0, 1, and 2, you see that the ocean is quite flat. Okay, and then of course as the wind increases, you see the sea that is in front of the house. The house is just on a small island, and the sea is becoming rougher and rougher. And this is by measurement of this roughness of the sea that the scatterometer will be able to provide information on the wind. So backscatter modulation by surface roughness. So when the sea is calm, so the blue arrow is the signal sent by the scatterometer, and the red is the reflection on the sea. So you see that no signal is coming back in the direction of the scatterometer. And then the signal is the normalized radar cross-section, as we call, will be almost zero. So when the wind is increasing, and now we get to go for 3, we start to have some small wave on the surface. And then, so not only the signal from the scatterometer in blue, not only reflect on the surface, but a small part of it is coming back in the direction of the radar. And as with Beaufort 6, when the wind increases, there is a more significant part of the signal that is coming back in the radar direction, and less that is directly reflected. And this is from the signal return in the radar direction that we measure the normalized radar cross-section. So you understand that this normalized radar cross-section will increase with the wind speed gradually. So now this normalized radar cross-section is not only dependent on the wind speed, but also on some other parameters of the radar, such as the radar look angle to the surface. So you see that the sensitivity to the wind of the radar cross-section is dependent on this angle of observation. So if the radar is looking straight down to the surface, like we can see here with the red and white, so then you have a small decrease of the normalized radar cross-section, sigma 0, when the wind increases. Okay? So that means that if the wind is very small, the sea will be flat, and then you will have a direct reflection of the radar pulse in the direction of the satellite, and then you have larger sigma 0, and then when the wind speed will increase, it will start to diffract in all directions, and there will be less return directly to the satellite. So now you see when you increase the angle, you go to 10 and then 20 degrees, the sensitivity is the opposite. It's like I was showing in the previous slides. So when you look on the side, the more wind, the more return you will have to the satellite. Because if there is no wind, you have a perfect reflection, and there is absolutely it reflects on the surface and go away, and nothing is coming back to the radar on the satellite. And for 30-degree incidence angle, so looking on the side, it's 30 degrees from the vertical, you see that you start to have a quite good variation and good sensitivity of the radar cross-section relative to wind speed. And it will increase also when you increase incidence angle. So that's why scatterometers are mostly concentrated on using side looking at these angles between 30 and 60 degrees. So there is also the sensitivity of the radar cross-section to the wind direction. Because when the wind is blowing on the surface, the slope of waves that are backscattering signal from the surface are not the same in all directions. Of course, there is more slope in the wind direction, because most of the waves propagate around the direction of the wind. And so, as you can see, when you turn around in azimuth, you will see that you have a change in the radar cross-section, which is maximum when it's facing the wind, and then minimum at perpendicular to the wind. Then there is a second maximum when you are going to look away from the wind, because you still see the wave but from the back face. And then low again at 90 degrees more, and so on. And the sensitivity is also a little bit changing with the wind speed, as you can see. So you have maximum sensitivity around 10 meters per second, and then with very high wind, the sensitivity starts to decrease with the direction. So with 30 meters per second, it's almost much less sensitivity. Okay, so now the reason why we get this backscatter echo from the sea surface is based on the resonance between the radar pulse and the sea surface. So here you can see the sea surface with a small ocean wave, and at the same time you see the microwave from the radar that is coming. And so there is a resonance between the wavelengths of the radar and the wavelengths of the wave. So the wavelengths of the radar is about, as you see, 2 centimeters. So and it's and for KU band and 5 centimeters for C band. It's a different frequency of scatterometer. But still, this will be resonant with very small waves on the surface. So this is the first mechanism, which is called Bragg scattering, and which is dominant for the large incidence angle. So that means that the echo that comes back to the satellite is caused by this effect. And that means that it will measure actually the very small waves. For angle less than 30 degrees, you have a little bit of specular reflection, which is direct reflection of the signal on the wave. Because if you have a wave that is sufficiently steep, there is one part of the wave that can be facing the radar, and then you have a direct reflection. But since the slope of waves are not so big, it happens only for significantly for angle almost close to the vertical. So, and this theory are used after to relate the echo, the intensity of the echo backscatter to the satellite to the actual shape and ocean wave state, which is at this in turn related to the wind. So, and then what we derive is what we call a geophysical model function. So it's an empirical function that relates the ocean wind that we need to extract and the wind direction to the backscatter cross-section measurement from the satellite. And you see that this is dependent, so of course, dependent on the wind speed, dependent on the wind direction, as we see, dependent on the look angle, the so-called incidence angle, but also dependent on the radar wavelength and on the polarization. Polarization is because the signal emitted from the radar is polarized either horizontally or vertically, and the return from the surface is not exactly the same with the vertical and horizontal polarization, because the geometry of the surface is not exactly the same also in the two directions. So this is just to show also that what we actually measure with the scatterometer is not wind, it's the small waves. And the small waves are forced by the wind. But the forcing of the small waves by the wind is not always constant. It depends, in fact, on the tension and and the tension, which is called tau here, depends on some parameter like the stability of the atmosphere. So stability is the difference of temperature between the air and the ocean. It depends also on the ocean current, on the air density, and on some parameter that depends on the sea state. So it's not a straight relation between the wind and the short waves. It depends on the actual friction of the wind on the surface, the friction which is at the cause of which is actually making the waves to develop. So the water density has a small impact on this forcing. So this is just a map of the sea surface density over the globe. So you see that it's almost everywhere the same. The variation is only 1%. Even if the colors are very different, you see that it's really about 1 kilo per liter. So the effect of the water density is small on the resulting wind speed. The effect is less than 1 meter per second. So we can neglect, in fact, this change in the mass density. So it also depends on the air density. So there is and the air density depends on the temperature. Okay, so when the air is warmer, the density is weaker, and then you may have a higher wind, and so the difference between the pole and the tropics is about 5%, and it will have an impact of 0.4 meter per second. So now we talk about the wind speed. So when we extract the wind speed from scatterometer, the information we get is so-called equivalent neutral wind. That means that we call it the wind at 10 meters above the surface, but in fact it is actually the wind that would be at 10 meters above the surface if the atmosphere was stable, according to the normalized radar cross-section observed by the satellite. And so this is, you see, this is dependent on Z0, which is the actual roughness, the surface roughness that is generated by, this is caused by the small waves. And so what is measured by the actual satellite is depending on sigma 0, and so it will change. It's not the same speed depending on the stability. So that's why we call a neutral wind measurement. Then if there is a different stability, we need to apply some coefficient to get to the true wind. So the surface roughness relates to the normalized cross-section, then depends on the friction velocity, which is this friction velocity, which is the effect of the wave, the tension of the wind on the surface. So at the end, you see that all the geophysical model functions are done by making correspondence between the normalized radar cross-section observed by the satellite and neutral wind speed. If you want to learn GMF, you absolutely need to use this neutral wind speed. So also the numerical weather prediction model, they usually ignore measurement, but the scatometer measures actually the forcing of the waves by the wind. So, and the forcing is only due to the relative motion of the wind and the current. So if there is a strong current in the wind direction, the scatometer will start to look and say that there is less wind actually than there is. So in fact, there is a signature of the ocean current on the scatometer data. This needs to be understood when analyzing wind scatometer from scatometer over ocean current area. So about geometry of the measurement. So these are all scatometer are polar orbiters. That means that they will go over the pole every 2 hours almost, and so they will turn around the Earth to be able to cover the full coverage of the globe each 12 hours. In fact, each 12 hours they provide a full coverage of the globe with ascending orbit and the 12-hour descending. So in 24 hours, you have a coverage in both ascending and descending orbit, as you see. So after 24 hours, you have more or less, except in some small area around the tropics, but you have a global coverage. So now, scatometer, they are made of antennas, and there are different types of antenna and different concepts. Here is 2 different concepts. The first one is a concept used by European Space Agency on the top, which is a fixed antenna on a satellite, but you put many antennas. As you see, there is 6 different antennas. Arrow. And you see that this allows you to look only in 2 bands of 500 kilometers, because we need to look on the side, as I was showing before, to have a good sensitivity. So we cannot look directly under the satellite. So there is a gap. There is a gap below the satellite of about I don't know, but maybe 500 kilometers, as you see in the middle, on the top, right? Where there is no measurement. Whereas in the other concept on the bottom is a rotating antenna. So it's just a very narrow beam that is turning continuously, and that allows to cover a much larger area, and there is no gap under the satellite. So this is the concept developed by the American with QuickScat, and that's been now used also by the Indian scatometer OSCAT and the Chinese H-Way2A. But the principle is the same, it's just that the antenna are working in a different way. So the European scatometer ASCAT, so he has three different antennas. And you see that it covers only bands on the surface, but not the full coverage. So there is actually 2 swaths, as I said, left and right. So this is the frequency is 5 GHz, so it is a C-band, which is 5 centimeter wavelength, about 5 centimeter wavelength. And of course, I will show that the C-band with 5 centimeter wavelength has less contamination by rain than the other KU band at 2 centimeters or 1 centimeter that is more contaminated by rain. So then this is just the concept. So after each swath is divided in vector, a few vector cells, and at the end you arrive to a resolution of 12.5 km. So in fact, this is just an overview of the processing chain for this scatterometer. So the input are of course the cross-section measured by the satellite. And then you have some pre-processing to filter out outliers, inversion that is using the GMF to transform sigma 0 into wind. Then some quality control, comparison with the model, ambiguity removal, because you may have ambiguities on the direction, and then some quality monitoring, and then finally you get the wind field. So of course, all these scatterometers are permanently checked again in situ measurements to verify accuracy and resolution. So as you can see, there are many buoys that are deployed in the ocean just to and they are used to verify this scatterometer. So this is a wind measurement at 10 meters above the surface or so. And then we make comparison. On the top is wind speed and wind direction, on the bottom is the two components of wind. Just to show that there is a good agreement between buoy and scatterometer, and this is constantly checked. And the resulting value are highlighted here. So for the European scatterometer, you have RMS error, RMS difference between the buoy and the scatterometer of about less than 2 meters per second. And for the American scatterometer, about 2 meters per second. So there are some other techniques to be able to, since the buoy have errors, the scatterometer have errors. If there is a RMS difference between the two, we cannot say that all the error comes from the scatterometer. So then we can use a triple collocation method. Then you need three different measurements. So here is the scatterometer, the buoy, and model. And from that, you can extract the actual error on each of the components. And then it was estimated that the scatterometer has, in fact, error that is below 1 meter per second. Even if the RMS difference with the buoy is 1.5. So then the final product is 12.5 kilometer. Sometimes it's 25 kilometer or 50 kilometer just by averaging. So you see, this is I think the first one is the 25 kilometer, and this is the 12.5 kilometer, where you have much more detail in the wind field, of course. Especially if you look below is a picture of the clouds, and you see that some of the wind field arrows are really following some details you see also in the clouds. So this is another example of our polar law, where you see that the 25 kilometer product is much less detail in the center of the polar law that when you use the 12.5 kilometer. So about quality control, of course, since the normalized radar cross-section can be contaminated by exterior effect, there needs to be some quality control. So what can contaminate the radar cross-section that would make it not not relative to the small wave, but to something else. So there could be some sea ice on the surface. So sea ice will either be will smooth the sea surface, or will, at the contrary, can sometimes be more roughness. There could be land contamination, of course, if you are near the coast. If you have also wind variability, then the radar cross-section will be very different in different area of your resolution cell, and then it can also provide contamination of the value of the radar cross-section. And finally, the rain. As I said, especially in the KU band, because there is more absorption of the microwave at KU band by the water, the suspended water in the atmosphere. So the C band is really going through the clouds much more without almost any attenuation. But for KU band, like QuickSat or OceanSat 2 or HY2A, you may have some attenuation of signal under the rain. So to detail, the rain effect can be a little bit complicated because there are several effects, in fact, of the rain. First of all, the signal can be attenuated as it goes through the cloud. And also this would reduce the backscatter and then reduce the final retrieve wind speed. But also, the radar can reflect on the raindrops if they are very dense. And then it will bring some extra scatter to the satellite. So this will increase the cross-section and increase artificially the wind speed. Sometimes a lot. And finally, the roughness of the sea is increased because the splashing of the raindrops. Sometimes when you have a rain dropping on the calm sea, you will start to see a lot of roughness on the surface just by the impact of the rain. And that can increase, of course, the roughness, not due to the wind, but due to this impact of the rain. But artificially, it will increase the local retrieve wind speed. So this is an example over a tropical cyclone, where you see on the left the wind field from the scatometer, and in some area very strong wind, so-called. But in fact, if you look at another instrument, another satellite that measures the rain on the right, SSMI, you see that it corresponds exactly to an area where you have strong rain. So in fact, this should be flagged in the final product and not given to the user as a wind information. So there is a automatic quality control that in fact check, because of course if the echo doesn't come from the waves but from the rain, it does not have the same dependency with the direction and the same dependency with the incidence angle. So since you have several measurements, you can do some consistency check and say that something is not looking good, and then you can start to flag. So this is where they put the small square. That means that it can be affected by rain. So there can be some automatic quality control to check for this way. So the limitation is, of course, near the complex weather situation. When you are around rain area, so you see that the same scatterometer data that is processed by different agencies will end up in a significantly different result around the wind front, because this procedure of quality control is not done the same by all the institutions. And sometimes you see the yellow dots means that it is flagged as a rain, and some others are not flagging them as a rain, so they say it's high wind, but in fact it may not be high wind but just rain. Actually, it looks like the one on the right is more realistic because they apply this quality control on the rain. So also discrimination of land and water and ice is also a difficult task. That is part of the quality control. So you may have information where is the land, for instance, but not always where is the ice. So it might be necessary to do some quality control directly from the information on the backscatter. So when there is ice, usually the backscatter is increased, but you need to have a quality control that says that this increase is not an increase of the wind, but it's just presence of the ice. So application of the scatterometer wind is mostly for meteorology, but not only. So of course, as you see, there are many measurements over land, but very few measurements over ocean. Just a few buoys, so scatterometers are used to fill this gap. So also, compared to numerical model, sometimes the numerical model they underestimate or overestimate wind, and this results in dramatic surge sometimes that are not forecasted, just because the wind was not correctly forecasted. And then that's why the scatterometer can provide complementary information. So here it's a case where the blue is the model and red is the scatterometer, and you see that I think the wind was underestimated by this by the model in this case. So the model also sometimes is missing some small storm. So when you see a small on the scatterometer that the wind is turning around some center, it means that there is a local storm. And in the blue, that is the model is absolutely missing it is the formation of a new storm, probably. Because it's not yet very circular, but there is starting to be some turning of the wind. So also identification of storms. So when there are storms that are with significant amplitude, they need to be tracked to anticipate when they will reach the coast and to anticipate the big waves that they may generate and send to shore. And sometimes these strong storms are not well forecasted by models. So here you see one storm in the North Pacific that is seen by two scatterometers. So QuickScat on the left and ASCAT on the right. So as you see, a big lack of this scatterometer is the coverage, because on the QuickScat you are lucky that you can see the storm, the whole storm, but on ASCAT you are missing the stronger part of the storm. So you may not say much with this scatterometer for this type. So this is why now they start to launch scatterometer with as wide coverage as possible to avoid this problem. Or to merge, I will show that you can also merge all the scatterometer data if you have different scatterometer at the same time to provide a consistent picture and fill all the gaps. So here an example also where you have atmospheric wave train that is missed by the model in blue, but clearly seen by the scatterometer. So the same now in QuickScat. So this was with ASCAT, and this is with QuickScat, and QuickScat was missing it. So because of we see a lot of flags. So that means that there were some uncertainty that are not been well extracted. So that means that not only you need to have a scatterometer, but you need to have a good processing of the data to retrieve the wind correctly from this scatterometer. So the polar law also is, as you see, there is a lack of observation, of course, of polar laws, and the numerical model prediction still have some error on the position and on the center of the pressure. And so the scatterometer is really bringing, when it's available, it's bringing a significant impact on localization of these polar laws. So some of you are working with the polar laws and know very well. So this is one example where the polar laws is well picked by the ASCAT scatterometer. As you see, it's really near the coast of western Norway. Okay. And we see that, in fact, the center was absolutely shifted on the IRLAM model, which puts the center of this polar law on shore, whereas in fact it's still in the ocean. And then that means that in the center, the wind is supposed to be low at the center of the polar law, and here, since it's misplaced, the model is giving a much stronger wind at the center of the polar law. So, since the scatterometer are only on polar orbiting satellites, the advantage of the polar orbit is that it comes more often. So there is more revisit at the same point when you are closer to the pole. And for the polar laws, of course, you may have more observation, several observations. Here it's 4 observations starting from 9 in the morning until 2 in the afternoon. So there is already there have been already 4 observations in the same area. So now going to coastal application, we see that scatterometer has very few information on near the coast. So that's why, first of all, you have a few information where you need to have much more information than offshore, because near the coast the processes are smaller scale, so they are changing faster. So you need to have a shorter revisit time than what you actually can get with the scatterometer. So you would need a constellation of scatterometer to really follow the coastal dynamic of wind, and that may have a strong diurnal effect and diurnal variation that you will not pick with only one observation every 12 hours, for instance. You would need much more. So when there is an observation, you can still get some dynamics near the coast with a special product that try to be a little bit closer to the coast. So it is a ASCAT coastal product. So you see that all the pink dots are measurement points that are not in the standard product, but it's a processing that is really taking care of the land contamination properly, and then you can get reliable information a little bit closer to the coast, you see, but not at the coast. So it's still maybe 25 kilometers away from the coast. So this is just to show that with scatterometer you can also quantify ice coverage, because ice has a significantly higher return than the ocean, so you can easily find the difference. And this is just two different extent of sea ice in March and in October, just to illustrate what this is. So this is an overview of what are the available scatterometer that can be used. So scatterometer data most of the time are free and open. So as long as there is a scatterometer mission, they can be used for scientific application, for instance, or operational application. So right now we are in 2013. So we get two from the European, METOP A and METOP B, flying in tandem. OceanSat 2 from India and HY2A from China. So there is 4 that are flying at the moment. But you see that in 2017 there will be 1, 2, 3, 4, 5, 6, 7, 8. So, but then in 2020 we don't know. It's too early because they need to find funding to look for mission and so on. So I see that there is also a Russian scatterometer to be launched next year. I don't know if you are aware, but you will be the prime user for this data in this room. Probably. Okay. So this is to summarize with the scatterometer wind. So the measurement that we get from scatterometer is the mean of the wind over the wind cell that is seen by the scatterometer. So it's a mean wind over, let's say, 25 or 12 km. It provides not true wind, but neutral wind, equivalent neutral wind. So if there is a air temperature difference between the ocean and the atmosphere, it needs to be taken into account when estimating the true wind. So there have been good verification with Buoy and numerical model. So the scales that are in the scatterometer are very close to 3D turbulence for small scales, which is expected, as expected. So there are limitations that we need to keep in mind. It can be contaminated by land. That's why it cannot be retrieved near the coast. It can be contaminated by sea ice and by rain. And also for very strong wind, sensitivity is much less. So it's difficult to measure and to calibrate the very strong wind. So most probably the very, very strong wind like hurricanes are underestimated by scatterometer. And are ambiguous is because the wind direction can sometimes be ambiguous on the scatterometer. But if you have several antennas like with a SCAT, you can resolve this ambiguity most of the time. So this is a further reference. So there is a website on scatterometry at KNMI with some user manual for the data and so on, so it can be useful. So there is also a forecaster forum that discusses use of scatterometer data for forecasters. So there are also some training material that you can find online on application of scatterometry, on some special case. So if you will get this link, you So there is a data available on the Satin server. Scatterometer data are from ASCAT, I think. QuickScat are available on the Satin catalog. So you may go and look first and then download the data from this point. This is locally here at the university. And there are some other area where you can access other type of scatterometer data that has been listed here. Final one is there is a yearly conference on ocean vector wind, and this is this year it was in the Netherlands, and they put online all the presentation where they discuss all the new advances on scatterometry and the new result and so on. So it can be also useful to check the presentation on this scatterometer conference. So maybe we can do a small break.
Yes.
Okay, and then we continue.